So yes, as Evelina said, the title of my talk's here, How to Deal with Privacy, Bias and Drift in Synthetic Primary Care Data. My name's Alan Tucker. I head the Intelligent Data Analytics Group here in the Department of Computer Science at Brunel University in London. What I want to do today, I'll try and keep to time as best I can, is to cover quite an ongoing long-term collaboration between me and the MHRA in the UK and the CPRD. So the CPRD is the main hub where primary care data is stored for most of England and Wales and some of Northern Ireland. So it's a very large data repository for primary care data. So what I want to do today is firstly kind of reflect on why synthetic data has become a hot topic and why we think we need it now, and how that demand for synthetic data has actually changed relatively recently. Then I want to do is talk about our approach to generating synthetic data, working with the CPRD, and how we've seen the importance of both the fidelity of that synthetic data and the privacy of that synthetic data. So these were the two key concerns when the project began in 2018. But also what we started to explore are kind of other issues that have branched off from that, having worked on this now for a number of years. And in particular, I'd like to talk a little bit about dealing with bias when generating synthetic data, dealing with geolocation, so geography, and the impact of location, and then finally talking a little bit about drift, the idea that data can actually change over time. So that's kind of the order, at least, of the talk. Okay, so the collaboration, as I said, began 5 years ago now with the MHRA and CPRD. And it was clear at that time that there was a need to address how to get useful healthcare data out to institutions like universities, but also the burgeoning health tech sector, and that there have been historical problems with trying to do that. So I don't know if people outside the UK may not know, but within the UK, this was big news over several years. There was a program in 2014 called Care.data, which was about trying to release personal healthcare data, making it relatively public. Medical record data, and I think it was literally a week before this was going to go live, it hit the headlines for all the wrong reasons and then kind of stalled. So it was clear that there's a lot of political reasons and essentially privacy concerns with releasing real healthcare data, and so that was seen as the primary driver for the project. But since then, we've really seen synthetic data being seen as more than just replacing real ground truth data. It's actually seen as a potential way of augmenting data to produce better models, or to improve at least that ground truth data in some ways. And here's just two examples: a headline in Forbes on the right, and a very nice publication from Nature about how synthetic data could actually be used to overcome some of the problems that we have with sampling and bias in real data. So synthetic data is clearly here to stay, but it's actually the reasons for needing it have data, synthetic healthcare data, using this very large-scale ground truth data set that's held at CPRD. Essentially, we found two key ways of doing this. One is to apply particular noise processes or jitter to the original data, so much so that it renders individual records. Continue like that.
Fingers crossed.
Yes, hopefully. Okay, so where was I? So at the beginning of the project, we explored this idea of noise processes and jitter, and applying those to underlying, ground truth data, or this idea of building generative models that would somehow kind of capture those correlations, distributional and relationships between features within the ground truth data. And we started off looking at different families of models. Here's just two examples, one that explored probabilistic graphical models on the left and one that explored generative adversarial networks on the right. And what we generally found actually for the type of data that we were working with, and that is essentially tabular data for the most part, as opposed to things like image data, that the probabilistic graphical models seem to work more reliably than some of the GAN approaches. That said, since then, there's been quite a lot of work in adapting particular neural network approaches to try to deal with tabular data. For example, the Van der Schaar lab at the Turing Institute have been working on a number of different synthetic data approaches, and in particular on tabular data. But that said, we did go ahead with this probabilistic graphical network approach to modeling the ground truth data held at CPRD. And that was for a number of reasons, as well as the fact that it seemed to handle tabular data well. It was also seen as a relatively transparent model. So we could see very much the conditional independencies that were stored within a model and be able to try to understand those to some degree. In addition to that, it's also a very flexible way of modeling data. So the idea of being able to model using these graphical approaches actually extends into the temporal domain. So things like state space models, dynamic Bayesian networks, or hidden Markov models also kind of lend themselves naturally to this approach. So we did that. We used a slight variation on a Bayesian network approach to modeling and generating synthetic data, which we published in NPJ Digital Medicine. We weren't the only ones, of course, and quite a famous approach known as PrivBayes also used Bayesian networks, but in conjunction with a Laplacian noise process as well. The unique component of ours really was the exploitation of hidden variables, of latent variables. So we used some classic statistical approaches to try to infer where there were likely latent variables influencing features within our data sets. And we did this because we know that there are, certain elements that weren't being measured within CPRD. There's always going to be some unmeasured effects. And we hoped that by doing this, we would get a better fit to the data. So this is just an example kind of network on a toy, a small subset of features from CPRD. And as you can see, we have lots of interconnections here which capture conditional independencies. And what this allowed us to do by inferring these kinds of networks from the data was to actually inspect those networks and look for potential spurious correlations or missing relationships. But what you can also see here highlighted in red is a number of latent variables associated with particular features within the data set. So it was quite nice, this transparent approach to modeling the data. It kind of instilled confidence in the underlying models that we were using, which could then be used to sample synthetic data in a very flexible and controlled way. So, for example, we could select from this model all women over the age of 60 who live in a particular region, and then sample synthetic data. So this idea of conditional generation of data. Okay, so we have this underlying model, but clearly we want to make sure that this model is capturing all of the essential relationships and biological dependencies and distributions that we see in the original ground truth data. So we call this fidelity, how it manages to faithfully reproduce those characteristics. And we've spent a number of years and published a number of publications exploring different ways of measuring fidelity. Everything from looking at simple correlational structures between features, extending that to partial correlations, looking at univariate distributions, looking at multivariate and joint distributions. And what we found is that we can indeed learn very high fidelity models which produce data sets, synthetic data sets that seem to capture all of those key expected relationships. And what's more, by using those latent variables, we do seem to capture a tighter fit to CPRD ground truth data. We've also experimented with extending this into the temporal domain. So as I said before, the probabilistic graphical model approach extends naturally into state space modeling, where we can capture, for example, signals of blood pressure changes over time. Obviously, then we can start looking at other metrics to capture fidelity. So things like autocorrelation and cross-correlation. And again, these approaches seem to do a pretty good job. So here you can see how similar the cross-correlation is between individual variables in the ground truth data on the right here against the synthetic data, and we have a very tight fit, and also autocorrelations here. So we seem to be capturing a really nice close fit to those underlying data sets. I would like to say, though, we are in a very privileged position having access to CPRD, which is it's a huge data set that spans decades and covers a very diverse population within England and Wales and parts of Northern Ireland. So this could be one of the reasons that it really fits this kind of modelling technique well. Ultimately, though, one of the reasons we were developing these synthetic data sets was so that people could validate their models. So you could imagine the health tech sector developing a new decision tool, AI decision tool, and they want to be able to test it on, something as reliable as a CPRD ground truth. So if we can make a synthetic data set available for them to, a company, for example, to be able to assess their models, and that assessment is very similar to the ground truth, then we've got something that's very powerful for those tech companies. And what you can see, for example, here, the left and in the center, is an example of ROC curves and precision recall curves. And the blue and the green are the curves for the validation using ground truth data at CPRD. I think that's the green, and in blue, our synthetic data sets. And so quite a relief that they sit very closely on top of each other. And capture quite a lot of the nuances in the shapes as well with precision recall trade-off. So we've been very pleased. I think CPRD were pleasantly surprised by how closely we could capture some of the characteristics of their ground truth data. Obviously, though, before we started to release this stuff, we wanted to explore whether releasing synthetic data was still a risk in terms of releasing, potentially private information, or at least information that you could infer about individuals or groups of individuals. So one of the things we started playing around with was just simulating attacks. So we assumed, for example, let's say an attacker knows something about an individual. So they may know a certain amount of attributes about an individual, maybe age, smoking status, region, gender, ethnicity, things like this. Using that information, we wanted to know, could they infer something new? So, for example, can they link that ground truth information to one synthetic data point or a small number of synthetic data points? So much so that if someone had some synthetic data, they could then infer something that could be potentially private about that individual. And what we generally found was, firstly, linking it to one or a small number of synthetic data points was relatively unlikely, but not impossible. So it did happen in a small percentage of cases. But even if you did that, and here's an example where you have ID1 and ID2, where the first ID is a ground truth real patient. So they were 88, they've got BMI of 23.9. You can see everything else from the West Midlands, and a synthetic data point, very similar features here. But when you actually go to the extra information the synthetic data holds, then there are differences. So the ground truth patient suffers a stroke and has a very different cholesterol ratio. So even if you can identify one relatively close by synthetic data point or cloud of synthetic data points, doesn't always mean that there is a direct risk of inferring something new. However, these kind of attacks are very, simulations are very ad hoc. But what it did do was provide CPRD and MHRA with confidence to be able to at least release some synthetic data sets under certain relatively light touch agreements. And so if you go to the MHRA and CPRD websites, you can now, with a small form, get access to cardiovascular disease data set, synthetic data set, and data based on COVID-19. And these are both considered high fidelity. We also have a medium fidelity data set, which is more just about trying to understand structure of some of these health data sets. That said, what we'd ideally like to do is make these data sets far more available. But before we do that, we need to start to understand a little bit more some of the more detailed mathematical notions involved with privacy. So, for example, things like k-anonymization and differential privacy. So this idea of if you can generalize data or remove key fields, can you then only identify a data point as being associated with k potential individuals? And differential privacy, this idea of being able to remove one individual from an analysis or modeling approach, should have no direct impact on that analysis. These approaches, they've got mathematical frameworks behind them, but they're not silver bullet. In fact, this idea of being able to actually assign a numerical value that people can, easily understand, that represents some level of privacy, is not really, it's not straightforward. In fact, we've started to work with Florent Hausziao from the Turing Institute too, using their TAPAS toolbox, which is a suite of simulations of attacks for testing for privacy. And this is still an ongoing project where we're trying to see how robust our synthetic data sets are to the identification of individual. Okay, so that was kind of the first phase of our project. Since then, there have been various other focuses, though, and in particular, I think bias was one of the key topics that really took off really 2 years in, and is still a major focus of our work. So, as we all know, bias has really hit the headlines to do with AI, mostly for the wrong reasons. This idea that when we use machine learning methods to learn things from data, the data that we're learning from often has inherent biases within it, which we should be aware about. We should be able to identify and hopefully try to find ways to mitigate those biases. In particular, COVID-19, I think, relatively recently, really sort of made clear within the UK some of the biases within our healthcare data. So as a result of this, it was something that we realized. We were releasing these synthetic data sets, and even though they're learnt, the models, from potentially huge data sets at CPRD, it doesn't get around the idea that they can still be biased. So we're still doing essentially secondary data analysis. So we wanted to start to explore this. How, firstly, can we detect these biases, and how can we resolve some of them? And bias can mean lots of different things. So, for example, it could be that there's spurious correlations, implicit correlations. We may have undersampling of certain populations within the data. There could be proxies for decisions within the data that could actually reflect, prejudiced attitudes. The labeling may be biased in some ways and could be inconsistent. So there's many different things that we could look at and see them as biases. So we've kind of focused at the moment. Firstly, we looked at, the idea of spurious correlations. And in actual fact, because we've been looking at these models in a transparent way, it's kind of helped us with confidence in identifying those. So these graphical models kind of help us identify whether there are, potentially problematic relationships within our models. So we felt quite confident about dealing with some of these spurious correlations. So our next focus has been on undersampling. So data is collected at CPRD from GPs, so primary care GPs within England and Wales. But the way that data is collected really could be prone to undersampling and biases in how that data is collected. So this has become the main focus of recent work. So dealing with undersampling is nothing new in AI and machine learning. And there's lots of methods, for example, trying to boost data, for example, when you're looking at imbalanced data for performing classification. So things like SMOTE or ADASIGN, which essentially try to boost data by adding actually synthetic data points within the data sets to balance the classes, or by adding noise. And so essentially what they're trying to do is oversample data so that you end up with, these underrepresented data points being boosted and being more equalized with the other data points to get a balanced class. What we've been interested in is something slightly different, though. We don't just want balance between, say, two classes. We want to try to just boost underrepresented populations within our CPRD data sets. So we've developed a method for doing that we've called Bayes boost. And we kind of have an advantage over some of those more basic boosting methods in that we have an underlying synthetic data generator. So this probabilistic model that sits underneath it can be used to generate new synthetic data points. So the overall idea within Bayes boost is essentially firstly to identify particular cases, so members of the public, population, who are difficult to predict for a particular disease outcome. So if we're trying to predict, let's say, cardiovascular disease or stroke, we say, well, which individuals have been difficult or uncertain in how we can predict them? So if we can identify those people, then we can actually compare those to the general population and then use our synthetic data generator to boost that type of population so that they're represented more within our data sets. And that's exactly what we've been doing with Bayes boost. So we've been using this underlying synthetic data generator to boost individuals who have proven difficult to predict. So what I want to show you now is just an example of Bayes boost in action. What we have here, firstly in green, is the distribution of a number of different ethnicities across the CPRD in the ground truth data. What we then have is using our probabilistic predictors, the distribution of those same ethnicities, but just for individuals who have proven difficult and uncertain to predict a particular disease outcome. So you can see those in yellow. Now, what we do is we say if the distribution here is for each ethnicity is higher than the ground truth distribution, then it means we actually need more cases of those particular ethnicities. So we need to boost those cases. Whereas if it's lower, it means we already have enough data to actually perform prediction and predictive tasks relatively well. So we can identify them based on that difference, and then we can use the synthetic data to boost those individual cases once they've been identified. And what we do is, again, we're not just doing this just to create balance, we're doing this to create models that are at least more representative of those underlying groups. But what we do find is when we do that, we do get dramatically sometimes in those individual subgroups, dramatic improvements in performance. So here you can see a jump from 0.795, I think, to 0.83 in accuracy. So it's sometimes really quite a dramatic improvement because we're identifying those difficult, underrepresented cases. And it's not just accuracy, of course, we can also see improvements in precision, in recall, and we've explored a number of different protected attributes. Like here is ethnicity for stroke, atrial fibrillation, and type 2 diabetes predictive models, but also gender we've explored region, and we seem to get consistent improvements when we identify those underrepresented cases. What we're now trying to do with this boosting approach is to apply it to kind of extreme small samples. We think it fits very nicely with clinical trial data, where what we can do is we can work with clinical trial design to be able to say, well, based on an earlier clinical trial, these kinds of people are needed to be able to improve the power of the predictive models that you want to build. But also we can use synthetic data to kind of build a representative control arm from an entire population, rather than these more kind of small control clinical trials we've seen before. So this is now a new project that we're starting in October to try to explore the impact of synthetic data and boosting on clinical trial data. Okay, the next thing I want to talk about is geography and location and the relationship with synthetic data. So it's clearly useful to understand the impact of geography on health. However, if we'd incorporated fine-grained location information from CPRD into our synthetic data generators, we really run the risk of much higher risk of identification of individuals. So what we've been interested in doing is seeing if we can use other aggregated data around England and Wales to help us allocate synthetic data that we've already generated regionally, so that we can then explore things like, regionalized health and how it varies. So what we've been doing is combining our synthetic data that's been generated from CPRD with aggregated data like the quality and outcomes framework, which is held at the GP level. So for every GP, we have a profile of information like the percentage of people who have suffered a stroke, the percentage of people who are over 85, registered at each individual GP. So can we allocate those synthetic data points around these GPs so that they create similar distributions and aggregated data, but at the same time don't run the risk of identifying anyone? And so we've come up with different ways of performing these allocations. And then we've assessed them because we do have the true underlying regional information. And so by allocating them like this, we can then do various things. We can look at the distributions that are actually held within the gold standard data here in green, and our synthetic data once it's been allocated using that aggregated data at the GP level. And we find very similar distributions, not perfect, but enough to make us think that this could be useful in exploring regional disparities of healthcare. On the right here, you can actually see the performance of machine learning models that have been trained regionally based on real regional information from ground truth data, but also then using our synthetic data that's been allocated using the GP information. And you can see that it's not always perfect. So for example, for Greater London, our models seem to perform much higher than the ground truth. So it doesn't perfectly mirror, but it seems to be capturing lots of the similarities in terms of shape. The nice thing, though, is that when you look at how synthetic data is allocated to the GPs, it doesn't reflect where that synthetic data that may have a regional tag associated with it comes from. So actually, it's distributing potentially similar synthetic patients from all over England and Wales to GPs at various points. So it doesn't kind of mirror, it doesn't just gather up all of the synthetic patients from one region and put them in that particular region, which gives us some confidence that this isn't running the risk of any of the privacy issues of allocating synthetic data with a GP from the outset. So this is an ongoing project. What we're now trying to explore is if we can build some truly regionalized models and incorporate some simulations of movements of people geographically around the UK for things like simulating pandemics. Okay, the last thing I want to talk about is drift. This has proved really important for applications with CPRD. So what I haven't said is CPRD releases its primary care data in batches, so it updates the data storage in batches, usually 6 months or 1 year intervals. And if the idea would be to create synthetic data that can be released so that universities, institutions, and the health tech sector can use it to develop AI devices for example, predicting, then it's really important that the regulation from the MHRA that goes with that is based on the performance of those AI devices. Unfortunately, as new data comes in these batches, these statistics could change. So, for example, the way data is collected may change suddenly. So you may have a sudden drift, like this example in the right-hand side here at the top. You may have incremental drift, like this third one down, where there's a slow change. This could be, for example, the introduction of vaccines during COVID, or it could be changing populations. So it could be an aging population means that there's a different probability of outcomes. So trying to deal with this drift and these drifts in performance statistics is really important in terms of regulation. So what we've been doing with the MHRA is trying to explore how regulation could be explored and what are the important components of regulation and how it would relate to some of the mathematical concepts of drift. So to do that, we came up with a very general protocol. So drift is a widely explored area of machine learning, so things like concept drift and data drift. But what we were interested in doing is really building something that's very general. And so we came up with this approach whereby we would sample from an initial batch of data and use those different samples to build a number of different predictive models. This would then allow us to take those models and predict and assess and validate a future batch. So let's say the next batch here, which we call the control set. So we get a distribution of some performance. This could be accuracy, precision, recall, it could be anything, F1, whatever you'd like. And then what we can do is we can see how these performances and these distributions of performances change with subsequent batches. And if these performances drift or are statistically significantly different over a period of time, then a decision can be made by the regulators to explore why that might be. It could be exploring the causes of the drift. It could be just re-updating the model with more recent data. But it gives at least a set of decisions that can be made once a trigger is set. And applying this simple protocol actually does highlight some nice things on real data. So on the left here, we applied it to cardiovascular disease data that was released annually. And you can see that it's relatively stable. We highlight two major drifts that are significant here, 2009 and 10, and they're the only ones. And it seems this could be to do with new guidance on statins that was released. Whereas you compare this to COVID, which we applied every month, it was a rapidly changing scenario with COVID, and you can see drift being recognized almost every time. So this is a very dynamic, changing set of data where the models are really struggling to keep up. And so it quite nicely shows you how important drift is, I think. What I want to talk about now, though, is really how drift and bias can interact. So what we found was even for cardiovascular disease, which you can see that original relatively stable performance on the top left, varies when you look at how it performs for different ethnicities. So here in B, you can see how the same model's performing. It finds a drift at the same sort of point in 2009, but a collapse in performance for Black Caribbean population. And with Indian, not so much a collapse, but a drift down, but the confidence intervals have become massively wider. So drift can happen in very different ways for these subpopulations. And it's really important that we identify those. And this is something that we're now working with the MHRA to specifically do when we're monitoring drift, to actually look to not just check if it's relatively stable over the entire population, but whether it's stable across all these subpopulations too. What we did find, though, and this was a nice kind of combination of that Bayes boost approach, was that maybe boosting some of the underrepresented samples, underrepresented populations using Bayes boost might stabilize some of the drift that we come across. And we found exactly that. So by boosting, you can see here, we didn't find drift anymore in all of the population or in the Black Caribbean community. So it's almost like by boosting some of these underrepresented samples, it overcomes some of the reasons that you might see drift. That said, underrepresentation in your data isn't the only reason that drift may occur. And you can see here in the Indian group, we actually see boosting doesn't get around this. And in fact, it finds new drift in here. So drift can occur for many different reasons. But if we have a more augmented, robust underlying data set, it can mitigate against some of the instabilities that we see in drift. Okay, just to kind of end, we've explored lots of different things to do with synthetic data, especially since that first release of those two key data sets. What we've been doing is publishing lots of stuff in machine learning journals and conferences in medical informatics, but we've also been publishing in the regulatory sphere as well. And we've had a number of publications in places like RAPS talking about some of these. We're recently just submitted to the Lancet about the impact of things like drift and bias and their interactions and what we need to be looking at when we're regulating. So to summarize, I think it's clear synthetic data is going to be useful, not only in validating models and allowing people access to realistic data sets that maybe mirror some of those ground truth models, but also to augmenting and improving models, maybe potentially better than ground truth. We've seen that this class of probabilistic approach generative models really do offer promise. They're transparent. You have quite a lot of control over how you model and generate data from those models. But whichever generative model you use, there's always going to be this trade-off between utility and privacy. So this idea that the more regional you may want to go, the more personalized you want to make your interventions, the more you want to handle things like rare disease, then there's more risk that you're going to be identifying individuals or small groups of people. And we haven't really solved this as a community. It's still a really important concept that we have to get this balance of how useful a model or a data set is going to be and how risky it is in terms of revealing potentially private information. But what we've also found with synthetic data is that bias is really important. It's not just about balancing difficult data sets, but it's also about identifying unwarranted links, understanding the semantics of models, potentially latent variables within your models, and exploring subpopulations and the impacts of models and data sets on subpopulations. We've also seen the importance of drift and how data, especially when it's coming out relatively, quickly, whether that's weekly, monthly, or annually, it's dynamic and data will change and populations will change over time. So it's important to identify these changes in performance in models that are built from synthetic data sets. So just a few bullets on our future work. We've talked about some types of bias, but there are others, as I mentioned before. We're very keen to explore labeling inconsistencies and labeling biases. We're also interested in identifying proxies for bias. I'll do a shout out for domain adversarial networks, which are really interesting ways to try to identify and mitigate potential proxies for bias that we're not even aware of in the data. We're also interested in combining some of our graphical modeling approaches with GANs by looking at some of these kind of hybrid models like causal GANs. We're very keen to explore extending Bayes boost to multiple disease outcomes and morbidities and multiple sensitive attributes simultaneously. As I mentioned before, we're really excited to explore this approach to boosting clinical trials and informing future clinical trials based on the potential biases and underrepresented groups that we discover using some of our methods. And clearly, throughout all of our experiments, a focus on fairness, transparency, and explainability has been key. So finally, just want to thank lots of people, and not everyone is here, but the key players in this collaboration. In particular, shout out to Pooja Miles, who's been really heading the CPRD collaboration with us, but also all of the team that's been working with us from the data science side of things. So thank you very much. Do we have any questions? And I apologize for the network issues that I had.